Hello, so in this video we're going to cover most of section 13.1. We're going to save some of the tricky examples to do in class, but this will go all the way up to and including example 13.7, which is most of section 13.1. So some of this unit is going to be review because we did a solutions unit earlier in the year, but we'll add on a little bit as we go on. But since the section 13.1 is mostly review of stuff we talked about earlier, that's why we're doing this as a video lesson. So first we're going to start off with a lot of terminology, some of which is new and some of which is not. So first off, if we're talking about our whole chapter being called solutions and their behavior, we probably should know what a solution is. A solution is just a homogeneous or homogeneous mixture of a solute and a solvent. Now we'll talk more about how they're held together later, but essentially the intermolecular forces that we talked about in chapter 11 are what hold our solutions together. Now remember that the solute is what gets dissolved. The solvent is the substance that does the dissolving. Okay, typically this is what's present in the larger amount, not always, but often. And water is one of the most common solvents we'll see. And of course we know that if we have water as a solvent, that would make it an aqueous solution, right? That's what that means. There we go. Okay. Now, the solute and solvent do not have to be a solid and a liquid. Technically, they could be any states of matter, and those will give us various different kinds of solutions. Now, when we talk about the relative amounts of a solute versus a solvent, we can talk about them quantitatively, which we'll do later in this section, but we also can talk about them qualitatively. So qualitatively, we could use words like concentrated and dilute rather than giving actual numerical values. So a concentrated solution has a lot of solute and a little bit of solvent, whereas a dilute solution has a little bit of solute and a lot of solvent. So you could imagine if you were picturing this in terms of making a mixture of Kool-Aid. A concentrated solution, it would be really, really dark. You would have used a ton of the Kool-Aid powder and just a little bit of water. And a dilute solution would be almost clear. You'd have just a little bit of the Kool-Aid powder and then a lot of water. Okay, so these are just some qualitative ways to describe concentration. Now, as I mentioned a moment ago, not every solution is a solid dissolving in a liquid. Those are the ones that we're familiar with just because when we did solutions earlier in the year, we spent a lot of time with aqueous solutions. However, we can have others. So if we think back to chapter 10, I can have a mixture of gases, which at the time we just called a mixture, and we dealt with Dalton's law when we were talking about our partial pressures. But technically that mixture is a solution. I have one gas mixed into another. Now a common example is air. So we know that air has all sorts of things in there. It's not just two gases. So we know that obviously oxygen is part of our atmosphere, but it's not actually all of it. So roughly we would say that there's about 21% oxygen gas, there's about 78% nitrogen gas, and then 1% of, we can just call them trace gases, which are just other gases that are in a very, very small amounts. So argons, there's some CO2, there's some pollutants, a little bit of everything. But this is just truly a mixture of gases. Now, if we're talking solvent and solute, typically the one that we have more of is the solvent. So in this case, we would probably say that our nitrogen is the solvent and our oxygen is the solute. But again, it's a little bit harder to tell when you have a pre-existing mixture like air, where not something that you're making manually. So, I mentioned this earlier as well. If I'm looking at a solution of liquids, you could either have two liquids mixed together, or you could have a solid in a liquid. So the one that we're familiar with from earlier in the year is that we had aqueous solutions, right? So in an aqueous solution, water is the solvent. This is the most common solvent, as I said. And again, we saw this way back earlier in the year, I believe in chapter 3. Okay, so that's one we're familiar with, but we could also have what's called a tincture, and this is when alcohol is the solvent. So these are used a lot more in medicine, so if you have ethanol or methanol or something like that as your solvent, okay? But the one we're most familiar with is an aqueous solution, which technically is usually a solid dissolved in a liquid, but you can, of course, have two liquids mixed together as well. And then the one that we spent some time with in our POGL is an alloy. So alloys are just mixtures of solids. So again, we might not necessarily have described them as a mixture previously, but now we know that an alloy is just a homogeneous mixture of metals. So these metals are combined together uniformly. They do stay together, and the different percents will give you different alloys. So some alloys you might be familiar with. So brass is actually a mixture of mostly copper and zinc. So there's our mixture there. Some other ones we're familiar with, bronze. So bronze is mostly a mixture of copper and tin. And you can, of course, add some trace other elements as well to change the properties, but that's sort of the major ones there. One other one, just so we can see it. So steel is another common one. Steel is a mixture of iron and copper, or excuse me, not copper, carbon. And if you change the percentages of this, you can actually have cast iron as well, but steel is sort of the common one there. So those are some examples of solid solutions, or what we would call them alloys if they are metals mixed together. Now, some other terminology. If we're talking about a solution, we can describe this solution as either saturated, unsaturated, or supersaturated. So what do those mean? A saturated solution is when you have dissolved the maximum amount of solute possible. So in other words, no more solute will dissolve because you've already dissolved as much as possible. So imagine when you were little, if you were making like iced tea or something, and you start mixing in a ton of sugar, eventually you're going to hit a point where you're just going to see solid sugar on the bottom of the cup. It will no longer dissolve. That's because you have made a saturated solution. The water has absorbed and dissolved as much sugar as possible, but it is not able to dissolve anymore. Okay? Or, for example, if you had a small cup of coffee and you tried to add 200 grams of sugar, not only would it taste bad, but also you'd have a whole lot of undissolved sugar on the bottom of the mug. Okay, so what we know is that for something to be saturated, you have to look at the specific solute dissolving, because depending on the solute, you may actually be able to dissolve more or less. We also know that saturation depends on the temperature. So for most things, if it's a solid, the higher the temperature, the more you can dissolve of a particular solute. The lower the temperature, typically the less you can dissolve. For gases, it's actually the opposite, but we'll come back and look at that more in a minute. So, also we know this word saturated. If you think about when it rains a lot, if you listen to the weather reports, they'll say that the ground is saturated with rainwater, and that's when you'll start to see standing puddles, because the ground literally cannot absorb any more water. So that's a saturated solution. Now, what about unsaturated? An unsaturated solution means you have less than the maximum amount dissolved. So in other words, you can dissolve more solute. So what would this look like? That would mean that if you added more of your solute, it would just keep dissolving and dissolving and dissolving until ultimately you hit the point where it is a saturated solution. And then you would start to see more solid left on the bottom of your container. Now, the one that's a little bit weird is a supersaturated solution. So we said that a saturated solution has the maximum amount of solute dissolved, but a supersaturated solution actually has more solute than should be possible. Okay, so you did dissolve everything, even though you're past what should have been possible. Now, essentially how this happens is you're tricking the solution, and the way you do that is by heating it and then cooling carefully. Okay, so for example, rock candy, if you've ever seen it. So if you've ever seen it, it looks like this. So rock candy, basically how this is formed, this is basically all just sugar with flavoring and some food coloring, obviously, for the color. But basically what they do is they'll make a solution of essentially sugar water, and they'll dissolve it until they've dissolved as much sugar as possible. Then they start heating the solution up. So as they heat the solution, more and more sugar is able to dissolve. Then, once they have as much of this dissolved as they want, they'll very carefully put this, the stick into the container. And then they very slowly and carefully, without disturbing the solution too much, allow this to cool. Then what they'll do is add just a little bit more sugar, which is usually called a seed crystal. And then all these crystals will start forming quickly on this stick. And ultimately, once all that sugar has recrystallized on the stick here, they pull it out, and that's how they have rock candy. So there's many other applications for this as well. So They actually use supersaturated solutions in some types of hand warmers, the ones that, when you break them, they immediately start the reaction. So there are a lot of useful uses for supersaturated solutions. But the idea is they are not very stable. If you disturb them or add even just a little bit more solute, typically crystallization will start immediately because the solvent doesn't want to have more solute dissolved than it should. Now, how would you test to find out what type of solution you had? If you add just a single crystal of your solute, which that's what I was saying is usually called a seed crystal, especially if you're purposely trying to crystallize it. If you add that solute and it dissolves, that means you have an unsaturated solution because the extra solute dissolved. If it just sits on the bottom and will not dissolve, that must be because you have a saturated solution. And if you have a liquid and you add more and then all of a sudden you see crystallization happening, that must have meant you had a supersaturated solution. So those are some examples of what you would see visually depending on whether you had a saturated, unsaturated, or supersaturated solution. So how can we actually look at this quantitatively now instead of just talking qualitatively? If you go to page 14 in the reference book, you're going to see a solubility graph that looks like this. So they're usually either called solubility graphs or solubility curves. Okay, but the moral of the story is they show a lot of different things. So let's look at some of the hints. So first off, note the axes. So we have temperature across the bottom, and then we have grams of solute per 100 grams of water on the other side. So notice that there are a number of different solutes on one graph. Rather than showing you one, you can see tons of them here. Also notice that we have some that are gaseous solutes and some that are solids. Notice that for the solids, typically as temperature increases, solubility increases. The more the temperature goes up, the more solute that will dissolve. For gases, it's actually the opposite. As the temperature increases, the solubility decreases. But that makes sense because we know that gases like to expand. So the higher the temperature, the more they're going to expand, and the less they want to stay dissolved in solution. So what are some tips as we look at our questions? So I just mentioned this one. Based on the slope, we'll see whether we have an increase or decrease in solubility based on temperature. So an increasing slope, so a positive slope would mean that you have increasing solubility, whereas a negative slope would mean you have decreasing solubility with increasing temperature. Now, notice that everything on this graph is based on 100 grams of water, so all of these are aqueous solutions, but they're aqueous solutions based on 100 grams of water, okay? If you are not dealing with 100 grams of water, then you're going to need to use a proportion to set up a different kind of relationship, and we'll see one in an example momentarily. The final thing is, if I want to use these terms, saturated, unsaturated, and supersaturated, what we're doing is comparing on the graph. So let's say that I was looking at this line right here. Okay, if a solution is described that's up here, I should only be able to dissolve for NaNO3 at 30 degrees about 93 grams or so. So if you have 120 grams dissolved, that's a supersaturated solution. So if my point is above the line, it's supersaturated. If I only have 80 grams dissolved at 30 degrees Celsius, that would be unsaturated because I could dissolve this additional amount to get to saturation. And if your point falls right on the line, you're describing a saturated solution. So let's check out a few examples. So first off, how many grams of sodium sulfate will dissolve in 100 grams of water at 10 degrees Celsius? So first thing I need to do is find my sodium sulfate line. And there are a lot going on here, so be careful, but sodium sulfate is this one. Okay, so if it's asking how much will dissolve in 100 grams of water, which luckily that's what our graph is already based on, we need to go to 10 degrees and then trace our line up right here. And we'll see that if I trace that over, again, this is just an approximate, but I would say that's about 57 or 58 grams of sodium sulfate. So that's how much will dissolve. And again, just a reminder, that's in 100 grams of water. If I had more or less water, that number would change. It would no longer be 57. Okay, well, what about this one? If you dissolve 85 grams of sodium nitrate in 100 grams of water at 30 degrees, how can we describe the solution? So, sodium nitrate, remember, would be NaNO3, so don't forget your naming and writing rules. So if I go to 30 degrees and trace up, so 30 degrees, trace up, NaNO3 would be right there. Now, our solution says we dissolved 85 grams here. So 85 would actually be down here. So based on where this is, if this is our line, but the solution we're describing only has 85 grams instead of about the 94 it's possible, this would be an unsaturated solution, meaning we could still dissolve more solute, okay? And that's because our point is below the line. So what about C? It says, how much potassium nitrate would you need to dissolve to create 135 grams of a saturated solution? Now, we're going to assume here that our 135 grams is actually the mass of water. Technically, we could reword this question instead to say, would you need to dissolve to create a saturated solution with 135 grams of water? But we'll clarify that for you on a test or a quiz, okay? But the issue is, this whole graph is based on 100 grams of water. So if I want to know how much will dissolve in 135, this is where the proportion would come into play. So I have 60 degrees right here, and I want to find the potassium nitrate line, which is this one right here. So at 60 degrees, I see that if I have 100 grams of water, I would have 110 grams of potassium nitrate in 100 grams of water. So how much would dissolve in 135 grams of water? Now it's just a matter of solving your proportion. So assuming you do your math correctly, pause the video for a moment, solve this yourself. All right, assuming you did that correctly, you would see that we could dissolve about 149 grams of potassium nitrate in 135 grams of water to create a saturated solution. So those were just some examples. There are, of course, many other questions we could ask you with solubility curves, but that's just sort of a sampling of what you'll see. Okay, now some other terms, and again, this should not be new. This is a review back from Chapter 3. We've seen these terms before, but remember that if you have a solute dissolved in a solvent, especially if it's a solid solute dissolved in water, we can describe that solute as either a non-electrolyte or an electrolyte. So, non-electrolytes do not conduct electricity, and the reason they don't conduct electricity is because they stay in their molecular form. So example, sucrose, it's all nonmetals, it will not separate, so it can't conduct electricity, there's no charge available to do that. Whereas electrolytes do conduct electricity, and that's because there are electrons essentially available to conduct electricity. Okay, because what happens is we have things breaking into ions, which would allow for charges and current to flow. Okay, now remember, if it's ionic, it has to be soluble in water in order to conduct electricity, otherwise it won't separate. So strong electrolytes completely break up into the ions they're formed from, so we would use a full arrow as opposed to like a double-headed arrow, which would show equilibrium. So an example here, if I write dissociation equations for these three, I know that aqueous KCl is going to break up into one potassium ion and one chloride ion for every one of those KCl formula units that goes into solution. Now, if the original concentration of KCl was 0.23 molar, if I wanted to know the concentration of K plus and Cl minus, because these are all balanced 1 to 1 to 1, that means the concentration of these will also be 0.23 molar. Okay. Now what about for the next one? So if we look at sodium carbonate, this is also soluble if you look at the solubility rules. So this would also completely dissociate, but because of the way this formula is written, I'm going to get 2 ammonium ions and 1 carbonate ion. Don't forget to include charges. Now, if my concentration is also 0.23 molar of this, because this is balanced 1 to 2, the concentration of this is going to be twice as much. So this would be 0.46 molar, but because these are 1 to 1, this would be 0.23 molar. Okay? So you guys take a moment, pause the video, and try to write a dissociation equation and determine the concentrations for the aluminum sulfate. All right, so hopefully this is what you found. This would break up into 2 aluminum ions and 3 sulfate ions. So remember, these brackets mean concentration. So the concentration of the aluminum ion would be the starting concentration times 2, so that. And then for sulfate, it would be the starting concentration multiplied by 3. So there we are. Okay? So there's a simple example with dissociation and concentration. Now, there are a number of other ways we can talk about concentration as well. So the first few will be review, and then we will see one that is new. So if we're talking about mass percent, we know that that would be the mass of your solute divided by the total mass of the solution times 100. Now, this is independent of temperature because we're describing one particular solution. So if I had a 5% solution of sodium chloride, that would mean that I had 5 grams of NaCl per 100 grams of solution. Now, assuming this was an aqueous solution, remember that that would mean 95 grams of water plus the 5 grams of NaCl. Okay, so that's what that would essentially mean. I could change that ratio, but at its simplest, that would be a possible ratio for a 5% solution. So take a moment, pause the video, and I'd like you to try example 13.2. All right, so this is what you should have had. So our percent would be the mass of the NaCl, our solute, divided by the total mass of solution, which would be the 13.5 grams of NaCl plus the 150 grams of water. Then we multiply by 100, and washing our significant figures to significant figures, you would get 8.3% sodium chloride by mass. So that's just a simple percent by mass example. Now our next type of concentration, so this was mass percent, the next would be mole fraction. Now we didn't talk about this earlier in the year, way back in chapter 3, but we did talk about this back in chapter 10, which was our gas laws section, right? So mole fraction is the moles of one particular solute divided by the total moles of solution, okay? So you could rewrite that like this if you'd like. Moles of solute by total moles of solution. And you do not multiply by 100 here, it's literally just division, so you're going to get a decimal answer. Okay, so if I had a solution made by dissolving 1.2 moles of solute in 16.8 moles of water, my math would look like this for that solution. Okay, I would do that, and we would divide and see that this would give us 0.0667. There's no unit on a mole fraction because you're dividing moles and moles and they would cancel. Okay, so that would be the mole fraction for whatever this solute was. Okay. So, knowing that, once again, pause the video and you guys try example 13.3. And this should be your solution. So the first thing is if I'm doing mole fraction, I need to actually have mole values. So I had to convert both of those masses to moles using molar mass. Then I would do the mass of one particular thing. So in this case, our solute, ethyl alcohol, over the total moles of solution to give us that. For water, it's the moles of water over the total moles to give us that. Notice if this is a 2-component solution, the mole fraction should always add to 1, and they do. Okay, now this is our new one. So we have not yet talked about this. We talked about molarity earlier in the year, but we did not talk about molality. So molality is the moles of solute, which that's the same, but this is the different part. It's per kilogram of solvent. So this is actually independent of temperature, which is going to be helpful for us later on. Molarity can vary slightly based on different temperatures because volume, as we know, can be affected by temperature, definitely for gases and slightly for liquids. So this one is fully independent of temperature. So if I had a 0.045 and we read this M there as molal, so whereas the capital M was molar, the lowercase m, I usually write it in italics, is molal, okay? But this would mean 0.045 moles of potassium iodide per 1 kilogram of our solvent. Now, if we assume that this is an aqueous solution, that would mean 1 kilogram of water, okay? So let's check out an example. If we look at 13.4, it says calculate the molality of this solution containing 50.5 grams of urea and 74.3 grams of solvent. So the first thing I do is as soon as I see molality, I write my formula. So molality equals moles of solute, which in this case is urea, per kilogram of solvent, which in this case says it's an aqueous solution, so that would be kilograms of water. Okay, so before I can plug into my formula, I do need to do some converting. So pause the video and convert 15.5 grams of urea to moles and 74.3 grams to kilograms. All right, so this is what you would get. Again, just converting grams to moles and grams to kilograms. So now I can actually plug into my formula. So our moles of our solute was 0.250 moles. Again, you should use the raw number in your calculator, but that's just the rounded value for paper. And then our kilograms of solvent Rather than writing the unit as moles per kilogram, you can do that, but otherwise we'll just write it as 3.36 molal, and typically you still write the solute afterwards. So it's 3.36 molal urea. So there we are with molality. Now our final concentration, and the last two examples we'll see here, is molarity, which we've seen this earlier in the year, so this should not be a surprise, but molarity is your moles of solute per liter of solution. This can depend on temperature, as I mentioned, because volume can vary slightly. So it does have its uses. It's one of the most common concentrations you'll see, but it is not foolproof. So if I had a 0.350 molar, remember we read this one as molar, solution of NaOH, that would mean we had 0.350 moles of NaOH per 1 liter of solution. So again, assuming this was aqueous, that would be NaOH plus water. Okay, so there are two examples, 13.5 and 13.6. These should be a review from earlier in the year, so I'd like you to pause the video and try both of these examples on your own. These will be the last two we will do. Here's your solution for 13.5. So you could do this two ways. You could either use this formula where you would plug 0.3 in for the molarity. You would convert this to liters and plug that in here, and then you would solve for moles and convert to grams. You can, of course, do that. The other way you can do it is you can use dimensional analysis, which will do all the steps together. So here's my volume conversion, milliliters to liters, so that I could then use my molarity, which that's what this is. Because remember that molarity is moles per liter, so I can use that as a conversion factor between moles and liters. And then here's our final step to go from moles to grams, giving us this number. Now the question actually asks you to explain, so explaining and saying 7.95 is not an answer. Explaining how I would prepare the solution is I would measure out 7.95 grams of sodium carbonate and then dissolve that in enough water to make 250 total milliliters of solution. So there's your example, your solution for 13.5. If you have not yet done 13.6, pause the video once again and try 13.6. And finally, here's your solution for example 13.6. So I solved this one with the formula. You again could have done this one with dimensional analysis, but just showing you the other way. I could have plugged in, since it's the same solution from 13.6, I know it's the same molarity. So I plugged in my 0.3 for molarity. I converted milliliters to liters and plugged that in here and solved for the moles. This is how many moles of sodium carbonate would crystallize. So to get the mass, then just converting moles to grams. So that would mean this amount of sodium carbonate could crystallize from this tiny 5 milliliter sample. So there are a number of variations that you could do with molarity problems as well, but there's just two. So at this point, that is most of section 13.1. Oops, I lied actually. We have one more section. Sorry, forgot about that. Last one was dilution. So when you have a dilution problem, we're using this formula, M1V1 equals M2V2, where this is what we would call our stock solution or the concentrated solution. Typically, you can make variations, but that's typically it. And then this side of the formula would be your dilute solution, so after you've already added more of the solvent. So our final example, this time for real, is 13.7. So you know that this is going to be a dilution problem because notice that I see two molarities. So I couldn't use the old molarity formula because there's only one molarity spot, but I have two molar amounts there. And then we see a volume as well. So pause this, and this is our final example. Try it on your own. And finally, here's how we would solve this. So note that whatever unit I put in here for the volume, which in this case was liters, is what this one will come out in. So I would get that for my answer. This was my starting concentrated solution, and we were trying to end up with this dilute solution. So that's why I kept these as the 2's and plugged the 1.33 in as the 1. So how would I prepare this solution? I would measure out this amount, so 56.4 milliliters, of the concentrated 1.33 molar solution, and then I would just continue to add water until the final volume was 250 milliliters. So now at this point, you're mostly done section 13.1. The final few examples we'll do in class because they are a little bit trickier. Thank you for watching. Please make sure your notes are filled out all the way up to and including example 13.7.